This is the 15th video in a series that I'm making to support a course in elementary number theory. And here we're going to look at solving polynomial congruences. So this is quite a bit more technical than solving linear congruences, but we still get a nice payoff. So we're going to start with something called Lagrange's theorem. So that involves a polynomial with integer roots. So I denote that by f of x is in z adjoin x. And it satisfies the condition that the leading coefficient is not divisible by p. So by the leading coefficient, I mean the coefficient of the highest power of x. Then the congruence, f of x congruent to 0 mod p, has at most degree of f of x solutions. Now we really want to compare this to what's going on over the real numbers. So notice that polynomials over the real numbers have at most degree whatever they are solutions over the real numbers. So somehow working mod p is fairly similar to working over the real numbers. Okay, so now let's look at the proof of this. And this will be by induction on the degree of f of x. So let's write that, degree of f of x, which maybe we'll just set to n just to make it easy. Okay, so let's look at our base case. So our base case will be the n equals 1 case. So notice in the n equals 1 case, f of x has the form ax plus b, and we know that p does not divide a. And so that means we're trying to solve the congruence. Ax is congruent to minus b mod p. But then by a previous video, we know exactly how many solutions there are for linear congruences. And in this case, there is exactly one. So I'll just write that down here, exactly one solution. And notice that 1 is most definitely equal to the degree of f of x in this case. Again, that's by a previous video, and we've done lots of stuff with linear congruences already. Okay, so now let's make an induction hypothesis. And the induction hypothesis will go like this. We want to suppose our statement is true for all polynomials of degree k, which is bigger than or equal to 1. And then we want to show that it's true for a degree k plus 1 polynomial. So let's consider f of x, which is a degree k plus 1 polynomial. And I won't write this down, but I'll just say it in words, where the leading coefficient is not divisible by p. So it satisfies the hypothesis over here. Okay, now I want to make the following observation. And that is, for all integers, maybe I'll call them m, we have f of x minus f of m has a root at x equals m. So we're not working congruent anything at this point. We're just working over polynomials with integer coefficients. Okay, so the fact that it has a root at that point means that we've got some sort of factorization theorem. And then again, this is like from an algebra class that you've probably taken earlier in your life. So that tells us that we can factor f of x minus f of m as x minus m times g of x. Again, that's part of what it means to have a root at x equals m. Now, we want to suppose that we've got some a where f of a is congruent to 0 modulo p. You might say, well, what if this congruence doesn't have any solutions? Then such an a does not exist, but that's okay, because if this has no solutions, well, 0 is most definitely smaller than k plus 1, and so our conclusion over here is satisfied. So we're assuming that we have at least one solution to this congruence. Okay, but now this kind of action is possible for any integer m. So the fact that it's true for any integer m means it's true for our integer a. So that means we can write f of x as x minus a times g of x mod p. Notice our f of a term, which came from that f of m with the m replaced with a, disappears because we're working mod p. That was our supposition up here. And then again, since the degree of f of x is k plus 1, this is degree 1, we have the degree of g of x is equal to k. So that tells us that g of x has at most k roots modulo p. But if g of x has at most k roots modulo p, and then a is an additional root for f, then that tells us that f of x has at most k plus 1 roots mod p. The k that come from g, and then the 1 that comes from this up here. Okay, now before we move on to our next result, I want to look at a case when we're working modulo not a prime and see that this is not true. Notice if we take x squared minus 1 congruent to 0 mod 12, we have 4 solutions to this. And our solutions come from the set 1, 5, 7, and 11. You can check that all of those square to 1 mod 12. And so that when you subtract 1, you get 0 mod 12. That means there are 4 roots, or I guess I should say at least 4 roots to this polynomial congruence, which is more than the degree of this polynomial, which would seem like a problem, but 12 is not prime, so it's not a problem. So in other words, this Lagrange's theorem really uses the fact that this p is prime. Okay, let's get rid of some of this, and then we're going to look at something called Hensel's lemma. Like I said before, now we're going to look at something called Hensel's lemma, which involves solving polynomial congruences modulo a composite number. But not just any composite number. This must be modulo some power of a prime. And the statement and proof are quite technical. That being said, the proof is really constructive, so it gives you a strategy for creating these solutions if you need them. Okay, so let's carefully look at the statement of this lemma. Let's suppose that f of x is a polynomial with integer coefficients, and f evaluated at a is congruent to 0 mod p to the m. So in other words, we have a root modulo p to the m already. Furthermore, we need to assume that f prime of a is not congruent to 0 mod p. Notice that's p to the first power, just the base power of p. Okay, then you might say, well, what do we mean by the derivative? This is just like the term-by-term standard derivative of a polynomial. Then there is a unique t, which comes from the set 0, 1, 2 up to p minus 1, such that f evaluated at a plus t to the pm is congruent to 0 mod p to the m plus 1. So let's look at this. This lemma gives us the ability to start with the solution mod p to the m and create a solution mod p to the m plus 1. So the idea goes like this. Let's say you want to solve some congruence like f of x is congruent to 0 mod p cubed or p to the 4th or p to the 5th. You start by solving the congruence f of x is congruent to 0 mod p. And you do that just like by hand. And then Hensel's lemma, or really more appropriately, the technique of the proof of Hensel's lemma, gives us a way to boost that solution to a solution of the congruence f of x congruent to 0 mod p squared. And then we can repeat that process to boost it to a solution of f of x is congruent to 0 mod p cubed, and so on and so forth until you get your desired power of p. Okay, good. So now that we've gotten this kind of like motivation taken care of, let's go to the proof. So we want to start by introducing some notation. So let's let n equal the degree of f of x. And then we want to expand f of x as a Taylor series. At x equals a. In other words, like centered around x equals a. So this is one of the very few times that we use any of the notions from calculus in this class. But generally, if you're like looking at a number theory class, then you've probably taken at least calculus 2. Okay, so that means we can write f of x as f of a plus f prime of a times x minus a. So that's the linear approximation, and then we can keep going. F double prime of a over 2 factorial x minus a squared all the way up to the nth derivative evaluated at a over n factorial x minus a to the n. And for an arbitrary function, you may have to worry about some sort of interval or radius of convergence, but since f is a polynomial, we don't have to worry about that at all. And now from here, we will evaluate at a special value of x that'll make this simplify quite a bit. And that value of x will be equal to t times p to the m plus a. Or maybe a plus t times p to the m if you want to make it look exactly like this right here. Okay, so let's see what that gives us. That'll give us f evaluated at a plus t times p to the m is equal to f of a. So that's obviously not going to change. And then f prime of a times t times p to the m. Notice the a and the a cancel when we do that subtraction. And then this is going to go all the way up to the nth derivative evaluated at a over n factorial, and then t to the n, p to the mn. So again, that's because if we do x minus a, this guy right here cancels. Okay, now this might look a little bit problematic because we've got these things in the denominator, but this is actually not a problem. So maybe let's do that with the following observation. And that is the kth derivative evaluated at a over k factorial is always an integer. And we can actually prove this by proving something quite a bit simpler. And I'll spell that out here. So we'll show this is okay for a function which I'll call g of x, which is equal to x to the r power. You might say, well, that seems a little bit like a cheat. But recall that our function f of x is just a linear combination of powers of x like that. So if this holds for x to the r, where r is arbitrary, then this is going to hold for our function f of x. Okay, so now let's move into the proof of this thing which is in peach with our function g of x. So notice we have g, the kth derivative of that, over k factorial, evaluated at a. So notice that's going to give us r times r minus 1 times r minus 2 all the way down to r minus k plus 1 over k factorial times a to the r minus k. Let's talk our way through that. So this numerator comes from taking repeated derivatives of this x to the r. The first derivative will give us the r, the second the r minus 1, the third the r minus 2, and then the kth will give us that guy way down there. Then the k factorial came along for the ride. And then each time we take a derivative, our exponent of x lowers by 1, giving us this a to the r minus k. But now let's notice that this stuff that I'm putting in yellow parentheses is in fact a binomial coefficient. That is the binomial coefficient r choose k. And then we've got this a to the r minus k going along for free. But binomial coefficients are always integers, so we're okay in that case. Okay, so no worries. All of these things just have integer coefficients. So that means this line right here might be something useful to work with. Let's go over here and look at our theorem, or our Hensel's lemma, and notice that our eventual goal is for this object to be congruent to 0 mod p to the m plus 1. So maybe we should take this line right here, which I'll star in purple, and reduce it modulo p to the m plus 1, and then somehow argue that we can pick an appropriate t to make that 0. So let's notice that f of a plus t times p to the m will be congruent to f evaluated at a plus f prime evaluated at a times t times p to the m. All the other powers of p will disappear because the next smallest is p to the m plus 1, because the next smallest is p to the 2m, which is larger than m plus 1, so that means it's 0 mod m plus 1. So let's just note here that we're working modulo p to the m plus 1. Okay, so let's summarize what we've got at the top, and then we'll finish this proof off. Let's recall on the last board, we did some trickery with the Taylor series, and we came up with the following congruence modulo p to the m plus 1. We've got f evaluated at a plus t times p to the m is congruent to f of a plus f prime of a t p to the m modulo p to the m plus 1. And our big goal is for this thing to be congruent to 0 mod p to the m plus 1. So let's see what it would take for that to happen. So in particular, we need this to be congruent to 0 mod p to the m plus 1. So that will occur if we have f prime of a times t times p to the m is congruent to f of a. I should say that is negative f of a mod p to the m plus 1. Okay, but that actually might seem a little bit problematic. Because we're still working modulo p to the m plus 1, we'd like to work mod something a little bit easier. And we can do that with a little bit of a trick. So let's notice that f of a is congruent to 0 mod p to the m. That was like one of our original assumptions, or one of the hypotheses built into the statement of our lemma. But what does that tell us? That tells us that p to the m divides f of a. But that means that f of a divided by p to the m is an integer, right? So those are all equivalent statements. Now from there, we can take all three parts of this congruence and divide by p to the m. So that produces like an equivalent congruence. Now, I think that was something that was proven in a homework exercise earlier. So just to see what we're doing here, we're going to divide this by p to the m, this by p to the m, and then this by p to the m. So that means this thing right here holds if and only if f prime a times t is congruent to negative f of a over p to the m modulo p. Now this seems a little bit sketchy because we've got a denominator here, and generally we're just working in integers. But by that pink discussion over there, we're actually okay here. Now we have to argue that this has a unique solution. So how do we know that this has a unique solution? I guess I should be more thorough and say I mean a unique solution for this t here. Well, let's notice by assumption, f prime of a is not 0 mod p. That's one of our assumptions that we haven't done anything with yet. So by some previous work involving solving linear congruences, we know there is a unique solution for t mod p. Okay, but that means that that solution can be rewritten from 0, 1, 2 to p minus 1, because those are all the residue classes modulo p. So now let's see how we would finish this off. We take that unique solution, which is a solution to this equation, which will be a solution to this equation before we divide it by the orange p to the m. But if it's a solution to this equation, that makes this blue underline 0. But the blue underline is congruent to our goal object, which means our goal object is congruent to 0 mod p to the m plus 1. That's exactly what we wanted to end up with. Okay, well, we're going to do a constructive example using this at the end of the video. But before we do that, I want to look at one more proposition. Building off of Hensel's lemma, we've got a proposition. And that is that the polynomial equation x to the p minus 1 congruent to 1 mod p to the m has exactly p minus 1 solutions. So notice this is saying that there are p minus 1, p minus first roots of the number 1 modulo a power of that prime p. And we can have any power of that prime p. Okay, well, how could we prove this? With induction, and we'll use Hensel's lemma. That's why we did Hensel's lemma. Okay, so let's look at our base case. So notice our base case will be the m equals 1 case. But let's recall that for all a from the set 1, 2, up to p minus 1, we know that a to the p minus 1 is congruent to 1 modulo p. And that's by Fermat's little theorem. Notice that there are exactly p minus 1 numbers that a can come from, but there are only p residues modulo p, and the one excluded residue is clearly not a solution because 0 to the p minus 1 is congruent to 0. It is not congruent to 1. Okay, so Fermat's little theorem takes care of the base case. So now let's make an induction hypothesis. And the induction hypothesis will go like this. So let's suppose for some k bigger than or equal to 1, we know x to the p minus 1 congruent to 1 mod p to the k has exactly p minus 1 solutions. Okay, cool. And now we're going to want to consider the next case. And now before we move on to our induction step, let's maybe name these solutions. So I'm going to name them x1, x2, all the way up to xp minus 1. So that means x1 to the p minus 1 is congruent to 1 mod p to the k, and then so on and so forth. We've got that for all of those. Okay, and we also want to notice that the other hypotheses of Hensel's lemma are also satisfied. So let's notice that if we set f of x equal to x to the p minus 1 minus 1, then, well, first of all, f evaluated at xi is congruent to 0 mod p to the k. That essentially comes for free from our induction hypothesis. And then f prime evaluated at xi is equal to p minus 1 times xi to the p minus 2. But let's notice that both of these numbers are relatively prime to p, and thus relatively prime to p to the k, which means when we take their product, it'll still be relatively prime to p to the k, and thus it's impossible for it to be congruent to 0 mod p to the k. So those are the 1, 2 hypotheses of Hensel's lemma. And now we can invoke the conclusion of Hensel's lemma. So Hensel's lemma will imply that there exists a unique, I'll call it Ti, it's going to come from the set 0, 1, 2, up to p minus 1, such that we know f evaluated at xi plus ti times p to the k is congruent to 0 mod p to the k plus 1. So what happened here is we took our solutions mod p to the k and boosted them to solutions mod p to the k plus 1. And how many solutions do we have so far? Well, we have at least as many solutions as we started with down here. We have at least p-1 solutions. Now we want to finish this by showing that we have all of the solutions. So let's suppose y is another solution. In other words, we have f evaluated at y is congruent to 0 mod p to the k plus 1. What we want is for this y to really be one of these that we've already constructed. Okay, so how can we get there? So this congruence right here tells us that f of y is a multiple of p to the k plus 1. But if it's a multiple of p to the k plus 1, that means it's a multiple of p to the k. So we know f of y is also congruent to 0 mod p to the k. But recall, we have all of our solutions to that congruence. And so that tells us that our y is congruent to x to the I mod p to the k for some I that brings it from this set. But now building Hensel's lemma back out of this, that means there exists a unique, I'll call it t, from the set 0, 1 up to p-1, such that y equals xi plus t times p to the k. But let's see what we've done. We used Hensel's lemma to create a ti for the xi, and then we used it again to create a t for this y, which happened to be congruent to xi. But then we know that those t's are unique. So this t is the same thing as this ti, which tells us this is equal to xi plus ti times p to the k. In other words, our new solution was actually one of our old solutions. And so that means we have all of the solutions for our induction step, and that finishes the proof of this proposition. Okay, so we're going to finish this thing off by looking at an example where we construct roots to a polynomial equation over a prime power setup using Hensel's lemma and the strategy outlined in the proof. Like I said before, we're going to finish this video off by constructing a solution to a polynomial congruence using Hensel's lemma. The polynomial congruence we'll look at is x squared plus 15x plus 31 is congruent to 0 mod 125. So that's clearly equal to 5 cubed. And this is laid out in 3 steps. First, you solve the congruence mod 5. Then you apply Hensel's lemma to boost that to a solution mod 25. And then you apply the technique from the proof of Hensel's lemma again to boost that to a solution mod 125. In other words, we go from 5 to 5 squared to 5 cubed. And if you needed to keep going, you could just reapply Hensel's lemma over and over again. Okay, so let's first introduce some notation. So let's set f of x equal to x squared plus 15x plus 31. And notice that if we reduce this thing mod 5, well, 15 is just going to disappear to 0 and 31 is 1. So that means we're really solving x squared plus 1 is congruent to 0 modulo 5. And there are exactly 2 solutions to this, which you can easily guess and check because 5 is a fairly small number. So here we have x equals 2 or x equals 3. And then you also want to check that if you take f prime and you evaluate it at 2 and 3, you do not get 0. That's another one of the hypotheses for Hensel's lemma. So we could work this off any of these roots, and if your goal in the end was to find all of the roots to our polynomial congruence mod 125, you would have to take every branch possible. But what we'll do is just go off of this x equals 2, and then maybe I'll leave as a warm-up to do the same thing for x equals 3 and see what final solution you get mod 125. Okay, great. So let's recall that mod 25, we're going to need to solve the following congruence. And this was built into the structure of Hensel's lemma, like I said before. So we've got t times f prime of 2 is congruent to minus f of 2 over 5 modulo 5. So again, I'll let you look carefully at that proof to see why this is the object we want to look at. So we need to calculate these two numbers, f prime evaluated at 2, and then f evaluated at 2 divided by 5. Okay, so let's notice that f prime evaluated at 2 is going to be the same thing as 2x plus 15 evaluated at x equals 2. We just used the power rule there. So let's see, that's going to give us 4 plus 15, or the number 19. But notice we can reduce that mod 5 because we're working mod 5, so this is congruent to 4 mod 5. So when we get around to it, we can replace this number here with just the number 4. Okay, now next we need to calculate this. So minus f of 2 over 5. Again, we might be worried that this is not an integer, but from discussion that we said before, this is an integer. This is okay. Okay, so let's calculate this. This is going to be negative, then we have 2 squared, which is 4, plus 30 plus 31, and that's going to be all over 5. That's what we get from substituting 2 up here. But notice that's going to give us negative 65 over 5, which is negative 13. But again, we only need to work modulo 5, so it's useful to notice that that is the same thing as 2 mod 5. It's 2 more than a multiple of 5. That multiple of 5 is negative 15. So just as we did with this thing right here, we can take this guy right here and exchange it for the number 2. So that means the congruence that we need to solve is 4t is congruent to 2 mod 5. But it's easy to check that a solution to that is t equals 3 from the theory of linear congruences. Okay, but that means our new solution, so I'll just call it new, will be equal to our old solution. So that was 2 plus 3 times the first power of 5. So in the end, that is 17. So in other words, at this stage, we know f evaluated at 17 is congruent to 0 mod 25. And now we can build this game again, starting with 17. And that's what we'll do over here. Okay, so again, following the structure of Hensel's lemma, we need to solve the following congruence. So we have f prime of 17 times t must be congruent to negative f of 17 over 25, and that has to occur mod 5. So again, this is just like some calculation. It's not too hard to do, but what we get is negative f of 17 over 25 can easily be calculated to be congruent to 2 mod 5. And then f prime evaluated at 17 can easily be calculated to be 4 modulo 5. So that means we need to solve, plugging those things in, 4t congruent to 2 mod 5. And this is just dumb luck that we end up with the same linear congruence that we did down here. Don't assume that's always going to happen. So that means that our solution for this t is t equals 3. And that means we can get our final solution. So this was like an intermediate solution. So our final solution will be our intermediate solution, which was 17, plus our value of t, which is 3, times our new power of 5, which was 25. So you can put all that together and see that you get the number 92. And now you can check that f evaluated at 92 is congruent to 0 modulo 125, which is exactly where we want to end up. Okay, so before we finish this thing off, maybe I'll give you some warm-up problems based on the stuff that we've talked about. Okay, so our warm-up just really involves the technical aspects of applying Hensel's lemma. So our goal is to find all solutions to the 3 polynomial congruences. So we've got x squared plus 4x plus 2 is congruent to 0 mod 7, 0 mod 49, and 0 mod 343. Okay, that's a good place to stop.